Hi.
Good afternoon.
What time does our test close?
5 o'clock.
Okay.
So let's see. So please remember to type a message in the chat whenever you get in as you're signing in type deal. So just whenever you get in, we will sign in the role. You can type your name, you can be present, whatever. That way we have a role for the day. I'm going to give another minute or so. So as a, I guess, brief little announcement, remember that you have a test up online that closes at 5 p.m. Make sure that everything is squared away and that you've done at least one attempt at it. Feel free to use the rest as you see fit. And again, it closes at 5 p.m. today. So get that taken care of. All right. So we've been talking about waves, and the thing we discussed last time was the velocity of a wave. So who can remind me what the velocity of a wave is in terms of wave characteristics?
You talking about speed over M. That's the M. I can't think of what the M stands for.
So those were we were doing units for
Okay.
that one. So velocity, the units of velocity is in most basic, it's meters per second. But we're talking about the velocity of a wave. So the first one we started off with is we talked about
Lambda.
Yeah. So the length or distance of a wave is the wavelength, lambda. That's the distance that the wave travels to complete one cycle. And then what is the amount of time required to complete one cycle called?
Delta T?
Not delta t. So delta t is just the change in time, if you're talking about little t. But the time that it takes to complete one cycle is called the period, capital T. But for various reasons, we don't like talking about the period of these waves. So we wrote it in another way. What was that other way?
Some 1 over F for T.
Yeah, so T is 1 over F. And
then it turned lambda F, right?
That's right. So the speed of a wave is the wavelength times the frequency. And it makes pretty good sense. The speed of an object is how far it goes and how often it goes that far. So if you go 10 meters 2 times every second, then it's 10 meters times 2, or 20 meters per second. So this is the speed of any wave in general. So electricity and magnetism come together to form waves of light. And these waves are very, very special. We won't get into how they're made too much. That's kind of what the other chapters that we are skipping over kind of discussed. But the idea is, just like anything else, how do you make a wave like a sound wave or a wave of an earthquake? How do you make those?
Repeat the question
It
again.
got something to do with like the vibration.
Perfect. Waves come from something vibrating. And vibrating is a kind of an all-encompassing term that means to move it back and forth really fast. Okay? So that's how when we speak, air goes over your vocal cords and it makes them jump back and forth really fast. How fast they jump back and forth is the frequency. The wavelength is a little bit different in that context, but it's the same kind of idea. So the frequency is how fast it's jumping back and forth. But that's moving around a physical thing. So if you move around a rope or a string back and forth really quick, that's what causes guitars to make noise. It's that wire jumping back and forth really quick. So when we jump to electricity and magnetism, it's actually made the exact same way. Except in order to exist in electricity and magnetism, you have to move something that has electricity on it, or mainly a charge. So if you take a charge, a little positive charge or a negative charge, it doesn't matter which, and you start to move it back and forth really fast, you create a wave that propagates out from that. This is how antennas work. I won't go into the math or anything, but if you have a antenna, or let's say a radio station, these things are huge, or the antenna in a cell phone, what it does is it makes one side positive and it makes the other side negative. And then An instant later, it switches them. So it makes the negative ones go up and the positive ones go down. And this is where the wave comes, is they move these things back and forth really, really fast. And it's just like if you were holding on to the end of a rope. I don't know if you guys have ever done that rope exercise, but the way you make a wave in the rope is you make your hand go back and forth really fast. And it pulls it up and then drops it. Up, drop, up, drop. And that repeated motion is what creates the wave. And it's the exact same thing with electricity and magnetism. Is we are bringing charges up, down, moving them up and down really fast creates this wave. So first thing, someone might know, it's okay again if you don't, but light has a very special property about it. Does anyone happen to know what it is?
UV ray?
I'm sorry?
UV?
Okay, so UV is a type of light. It's a certain frequency or wavelength, depending on how you want to say. So it's a certain kind of light, but all light, whether it's UV or visible or radio waves, everything, light has a very special kind of property about it.
Because UV stands for ultraviolet.
Yeah, UV stands for ultraviolet, but this special property we call C. And it is 3 times 10 to the 8th
Oh.
meters per second.
Whoa.
What is that unit? What thing has units of meters per second?
Velocity?
Perfect. The velocity or the speed of light is constant. It doesn't matter anything. There are some minor differences, like if you're going through a material, the speed changes, but going through the air or space, the speed of light is constant. This is definitely something that you're going to want to remember. And it's technically like 2.98 times 10 to the 8th, but we're using 3 times 10 to the 8th. So this is the speed of light, of a wave of light. Okay? What did we say about wave speed? I'll get
That it's
what is the speed or the velocity of any wave, period?
Zero.
Second.
I don't know. Is it
Lambda
zero?
F.
Second or lambda
Lambda
times
F.
F or T.
Lambda F.
times-
Period. Always, always. Well, if lambda times F is the speed of that wave, and for light, it is constant, or C, what this means, or one of the things that this means, is that if you have a frequency of light, then the wavelength is also constant. So you can't have different wavelengths for different frequencies. So since lambda f is always c, then if you have lambda over c, you can change this equation to lambda equals c over f, or f equals c over lambda. Okay. The point is that for any wavelength of light, there is a specific frequency, and vice versa, which is very different from other kinds of waves. We didn't get to talk about them, but you can have different wavelengths with different frequencies end up with the same velocity in other terms. But for light, every wavelength of light has one frequency, and every frequency of light has one wavelength. So when we talk about light, just know that if you have the frequency, you also have the wavelength, and vice versa. If you have one of them, you have the other one by this little relationship. Okay? So that's one of the qualities that's very important. The other one has to do with, it's kind of interesting where this C comes from, but it is a constant. But there were two other constants that we talked about when we were doing electricity and magnetism. Does anybody remember what the name or symbol of the constant that dealt with electricity was? What is the electrical constant? Okay. Electricity.
K.
It's not K. That's close. K is a simplified version of it, but it's the other one with K. So
Boltzmann?
no. So what did K equal?
Okay.
1 over
You talking about it says the value of
1 over 4 pi
yeah.
E0.
Yeah.
E0 epsilon naught.
Yeah.
Yeah, the Coulomb constant somewhere I don't pronounce like that.
Yeah,
It's
the Coulomb constant
Coulomb's
value
constant.
is
Yeah,
9
Coulomb
times
constant. Yeah.
10 to the 9th.
But it is the permittivity of space. The more technical definition of it, but it means epsilon naught is basically how easy it is for electricity or an electric field to exist in space. It's just how easy is it for electricity to exist. Okay, with this in mind, there was a constant for magnetism. What was that one?
constant for magnetism.
So electricity had an E.
Yeah.
What do you think magnetism is going to have?
An M.
A mu. And this is the permeability
A U.
of space. It's not a U, it's a mu, which is a
U.
Greek letter. It's a lowercase mu, and it's the permeability of free space. And in the same vein, it is how easy is it for magnetic fields to exist in space. So how easy a wave travels through something, how quickly a wave travels through something, is directly related to how easy it is for that wave to exist in that thing. And this is actually where the speed of light comes from. And this is a big deal, but these two things combine together, epsilon naught times mu naught,
One over C squared.
So this was a very big find when it came about. This isn't exactly, obviously, how it did. But this was part of the proof that light was made up of electromagnetic waves, because its speed is entirely dependent on how electricity exists and how magnetism exists. So this is one of the key factors, is that those two constants are directly related to back to light. But this is the speed of light. So let's see. How do we want to proceed from this? We want to talk about the spectrum. All right. So we have this little relationship, C equals lambda F. So that means that every frequency of light has a specific wavelength and vice versa. We're going to see what that means. So I'm just going to share this picture. So this is the spectrum of light. I know the thing is a little bit tough to read. There's a lot of information in there. But if you look at the top, you have the two labels. So you have a frequency in hertz, which means 1 per second. And then you have the wavelength. And this is picometers, nanometers, micrometers, millimeters, centimeters, meters.
Meters and
So
kilometers.
this means that the wavelength goes up or increases as you go down it. And on this one, frequency goes up as you go up. So part of the thing with this C equals lambda F is that if you make the frequency bigger, you have to make the wavelength smaller, and vice versa. because when you multiply them together, you have to get the same number every time. So visible light is this tiny little spectrum right here. This is everything that you can see. So this is
Like
a kind of a little pop out. Everything that you can see has a wavelength between 400 nanometers and 700 nanometers. All of this stuff out here is everything else. So ultraviolet right here, and infrared. So it's a little bit awkward to understand, but what does ultra usually mean? Something is ultra,
like even more large.
yeah, bigger, super, awesome, huge.
Yeah.
And that's the weirdness is people usually like to think of light in terms of wavelengths. But if you look at it, ultraviolet has a 1 nanometer-ish spectrum. So whereas visible light is 400 to 700 nanometers. So visible light is much larger in wavelength than ultraviolet. But these names are actually determined by frequency. So ultraviolet has a larger frequency, 10 to 17, 10 to 15, than visible light.
Okay.
The same thing with infra. Infra actually means below. And so ultraviolet has frequencies above visible light. Infrared means that they are below visible light. And violet and red are just the two ends of the spectrum. Ultraviolet means it's above violet, which is at the top.
Yeah.
Infrared just means below red, which is at the bottom. So now we have, if you keep going up in wavelength, you have microwaves, which are exactly like the waves in your food or in your food processors.
Yeah.
Then you get to TV and FM radio.
Radio waves.
And you get even further and you get into AM. So the wavelength of an AM radio wave, so if you flip to that dial on your car that you never use, those waves are about a kilometer long. That is huge. It's about 3/4 of a mile long. So they are massive. But this is the thing, they're all light. You just can't see them because they are way outside the visible range of light, but they are still light waves. So this is where we talk about, how light is everywhere. It's all around you, this kind of thing. But I want to take some time to, I guess, hammer home this idea that how frequency and wavelength are related to each other. So let's look at this little quick quiz here. And so the higher the frequency of light, the longer the wavelength. Is that true?
Let's see. Which of the following statements are true about the light waves?
So remember, this is all based on C equals F times lambda. So if you have a really big F, what does that mean about lambda?
Wouldn't the shorter wavelength mean it's like higher frequency because like when it's frequent, it's like going really fast, so it's making them fast like on a graph?
Okay, so that's a very interesting way of putting it. You're correct. Higher frequency and shorter wavelengths come together, or they are associated. The algebraic way to think about it is these two things have to multiply together to give this number. So if I take F and make it big, then if I don't change lambda, then C also gets big. So let's say 1 equals 1 times 1. So that fits.
Yeah.
What if we make the frequency 2? What happens to the wavelength?
Hmm.
It becomes 2.
It becomes 2. 2 times 2 equals 1.
It
So zero
becomes
so
one
equals
half.
4.
It becomes 1/2.
It becomes
Yeah,
1
1
half.
Yeah.
So if you make frequency big, you have to make wavelength small. So A, higher frequency, big F, means small lambda. So that is not true. Well, let's look at the other ones. Little f means big lambda. Is that true?
No. Because I think E is true because the lower the frequency, the short the
Well,
wavelength.
we're going step by step through them. B.
All right.
If you make f small, that makes lambda big. So that's true. Because for the same reason that we just said, if we make frequency 1/2, so if we make the frequency instead of 1, we make it 1/2, we make it small, then we have to make the wavelength bigger. So I want to go back to what was said a second ago. I can't remember who said it. Who mentioned they're happening more often or something like that?
Destiny.
Yeah.
Yep.
Okay. So I like that thought process because it gives a good visual of it. So let's say that this wave travels this far in 1 second. Then if you have a wave that is shorter, so this wave is half as big, in order to get to the same end point, maybe I should have done that in a different color. It had to do 2 cycles, right? So its wavelength is half. So the blue wavelength is half the big one. But in order to make it to the end at the same time, remember they have to be going the same speed. In order to make it at the same time, what does the blue wave need to be doing?
Going at the same frequency?
Because if it goes at the same frequency, which is 1 cycle per second, The black one has a frequency of 1 per second. Now, if the blue one has a cycle of 1 per second, it's going to end up here when the other one is here. So it needs to do 2 cycles in 1 second. So the blue frequency,
So it needs to go half the frequency the first one goes.
it needs to go twice the frequency.
Fast.
So it always goes twice.
Doesn't always go twice.
Oh,
It goes, its frequency is twice as much because its wavelength was half as much. Does that make sense?
yeah.
So it's the same idea over here. If we make the frequency half as much, then we need to make the wavelength twice as much, or vice versa. If we make it twice as frequent, then it needs to go half as far. So, but I really like the visual representation of it, because if the thing, it's kind of like, maybe a good way to think about it is short people walking with tall people. So if a short person and a tall person are walking down the street, the short person has smaller steps, right?
And the big one
person
has
has a-
big step.
Yeah, it's called their gait or their stride. So in order for the small person to walk the same speed as the big person, what does the small person have to do?
Walk twice as fast.
They have to take twice as many steps in the same amount of time. So they have to move their legs twice as frequently. I know it sounds weird to say that, but
Like
walk
twice
twice as
more.
fast means you're changing the speed of your walk. We're not changing the speed, we're changing the frequency of our steps. So this guy walks 3 steps, and then the little guy walks, I don't know, 4 steps per big
Second.
step.
Oh,
So in order to go the same distance,
That's so selfish, bro.
in order to go the same distance in the same amount of time, or to have, which is the same thing as to say they have the same speed. If he takes 3 steps in 3 seconds, this person needs to take 12 steps in 3 seconds. So wavelength is how long their step is, and frequency is how often they step, which is why in cartoons everybody makes fun of the short people and their legs going like crazy, because they have to take a bunch of tiny steps to match the big steps. But
yeah.
that's a great analogy that I've never really thought of until you made that comment. So tip of the hat. But we're about to get kicked off, I think. So please make sure you get your test done. And then we will continue with this stuff on Monday.
Monday.
We need to do the mind taps that are with the book?
What?
Do we need to do the mind taps that are inserted with the book?
What do you mean?
No.
Oh,
No, yeah, no.
You
no,
doing
no.
too much.
No. No.
Oh,
I don't
man.
even know what you're talking about. So
We just
I
got
ain't even know what
Oh,
you're talking
man.
about.
Come on, man.
Hey, I can only hear one person at one time. Everybody yelling at me. Destiny, what are you saying?
No, I wasn't yelling at you. I was saying